Thank you very much, and it's a pleasure to have the chance to give this lecture. And I want to thank all the, not just lecturers, but many of the participants for the good questions you've been asking. So you've been hearing something about topological string theory in 2 lectures by Hiroshi Uguri. And if you emphasize the topological viewpoint, then you would say that in topological string theory, you're counting holomorphic maps from the string worldsheet, which is a Riemann surface of genus G, to a target space Y. And Y is fixed, but in string theory you integrate over the moduli space of the worldsheet. So you don't say what the complex structure of the worldsheet sigma is supposed to be. It can have any complex structure, but you ask that it should have some holomorphic map to Y. So if you are given a map to Y, it has winding numbers. It will, in general, map around 2-dimensional cycles in Y. If the second Betti number of Y is 1, the winding number is just an integer. But in general, the second Betti number is bigger. And to describe the map topologically, you have a whole collection of winding numbers that make up a vector of winding numbers that I'll call D, an element of H2 of Y with integer coefficients. It measures how sigma is wrapped around various cycles. And then, to compute the topological string theory partition function, for every genus of the worldsheet and every winding number D, you count the number of holomorphic maps with that homology class where sigma has genus G. Now, I put the words count in quotes because the proper counting here involves a lot of technicalities. In fact, one of the things that Gopakumar-Vafa did with their formula was to explain a better way to avoid some of the technicalities. But if we had time, I'd go on maybe and explain at some length what's meant by this counting. But for today, we will just not worry about exactly what it means, because we will approach the subject from another way. Now, before I go too much farther, I should say that the talk is based on a paper that will appear with the student, Mykola Dedyshenko. So we had these winding numbers for the worldsheet. We introduce a set of coupling constants that's dual to the homology class. And then we define the genus G topological string partition-free energy. I started to write partition function, but partition function would usually be the exponential of the free energy. What I'm defining here is better called the free energy. So I just forgot to remove the word partition. So the genus G free energy you define by summing over all winding numbers, and then you have the number of maps with that winding number, and you weight each one with the exponential of the classical action. But the classical action, if you define the t's correctly, is just a constant times the winding number dotted with t. So Uguri has set up the machinery where you show that there aren't any quantum corrections to the classical action, and the classical action can be written this way. T are the Kähler parameters that were in Uguri's lecture, and D are the winding numbers. So for my lecture today, all you need to really know, you don't need to know the details of this function, but there is such a function that you can calculate by counting holomorphic maps of a specified genus and also a specified degree to a target space Y. Then the full topological string partition function, same slip as before. The full topological string free energy is the sum over genus of the genus G thing times G string to the 2G minus 2. So that's the full free energy, and then the partition function, including disconnected contributions, is e to the f. Now, what does topological string theory have to do with physical string theory? Because today's lecture will really be about physical string theory. That's why I'm not going to take the time to explain some of the details about how the number of maps is defined. There's actually a remarkable answer to this that was proposed by Brzezinski, Cecatti, Uguri, and Vafa. Uguri mentioned the reference this morning, and it was confirmed in a very hard calculation by Antoniadis et al. So here we consider type 2A superstring theory compactified down to 4 dimensions on a Calabi-Yau manifold Y. This case is important both in physical string theory, where you actually have heard about it from Martin Weinhold. It's used to make semi-realistic models of particle physics, And it turns out to be a particularly interesting example in topological string theory. These facts are kind of the same facts because, as I'm about to tell you, there's a link between the topological and physical string theories. So it's no coincidence that, well, the very rich properties in topological string theory are related, certainly, to the role it plays in making semi-realistic models of particle physics. Now, in type 2a compactified on a Calabi-Yau, so B2 is called the second Betti number of the Calabi-Yau. It's the number of two-dimensional holes or cycles that our string worldsheet could be wrapped on. So that vector of winding numbers, D, has B sub 2 components. And there are B sub 2 plus 1 U1 gauge fields that come from the Ramond-Ramond sector of superstring theory. One of them is distinguished. It's the Ramond-Ramond gauge field that we already had in 10 dimensions before any compactification. But when we compactify, we get B2 more U1 gauge fields, and they arise as follows. There's a Ramond-Ramond 3 form that I'll call C. You make a Kaluza-Klein expansion where you write it as a sum of terms. Each term is a 2 form on the compact manifold, omega I, and the AI are then gauge fields on R4. So the second Betti number is simply, by definition, the number of independent 2 forms that can appear in this expansion. So it's the number of U1 gauge fields in 4 dimensions. So altogether, we have B2 plus 1 gauge fields. 1 is distinguished. It was there before any compactification. And B2 more come from the compactification. Now, type 2a on a Calabi-Yau manifold has 8 unbroken supersymmetries. So we can describe the space-time effective action in a superspace with 4 bosonic coordinates and 8 fermionic coordinates. But it's convenient to break up the 8 fermionic coordinates according to their chirality. So in 4 dimensions, we have spinors of positive or negative chirality. So we have 4 fermionic coordinates of negative chirality and 4 more of positive chirality. All the indices are 2-valued. The spinor indices are 2-valued because spinors of definite chirality have 2 components in 4 dimensions. But you have to remember that we're doing n equals 2 supersymmetry. Type 2a on a Calabi-Yau has n equals 2. So there are actually 2 spinors of one chirality and 2 spinors of the other chirality among the fermionic coordinates. So there's no symmetry that acts on the index I. There could have been an R symmetry, but generically there isn't in type 2a compactification on the Calabi-Yau. A chiral superfield is a function of x and the thetas that doesn't depend on the theta bars. An anti-chiral superfield is a function of x and theta bar that doesn't depend on the thetas. A generic superfield is a function of all 8 fermionic coordinates as well as the bosons. Now, of the B2 plus 1 U1 gauge fields, B2 linear combinations are in vector multiplets. But there's something different in n equals 2 compared to n equals 1. So what I call a chiral superfield actually describes a vector multiplet. And that's because if we did n equals 1, we would make the theta expansion. It would stop after 2 terms. And the term up here would be a scalar, a spin 0 field that's an auxiliary field. But with twice as many thetas, I haven't written out all the Lorentz indices, but this term is more complicated. And it includes the self-dual, or the anti-self, in my convention, it will be the anti-self-dual part of the field strength of a U1 gauge field. So for n equals 2, what I'm calling a chiral superfield describes a vector multiplet that includes a U1 gauge field. So there are B2 U1 gauge fields in vector multiplets, but there's one more U1 gauge field that's not in a vector multiplet. It's part of the supergravity multiplet. Because the supergravity multiplet for n equals 2 supersymmetry in 4 dimensions contains a U1 gauge field also. And that one is called the graviphoton. It's the photon in the gravitational multiplet. Sorry. My terminology has been poor. A chiral multiplet doesn't depend on the theta bars, but it didn't have to be spinless. It might have carried spin. So the vector multiplets are in chiral multiplets that are spinless. The graviphoton is also in a chiral multiplet, but it's in a spin 1 chiral multiplet. So I write the spin 1 chiral multiplet as curly W AB, where A and B are spinor indices of negative chirality, and this is a symmetric bispinner, so it has the quantum numbers of an anti-self-dual gauge field. And its bottom component is the anti-self-dual part of the graviphoton field strength. The details of this are not too important for the lecture, except all you have to know is that there are these chiral superfields that describe all the gauge fields but one. But there's one gauge field that's in the supergravity multiplet, and it's in a different kind of chiral superfield. So in the rest of the lecture, when you see curly W, it contains the graviphoton, and when you see curly X, it contains all the other U1s. Now, in general, actually, as Natty explained in his first lecture, Natty Seiberg, in a supersymmetric theory, a term in the effective action might be a D term, meaning it can be written as an integral over all of superspace, which in our case would mean an integral over 4x's and 8 thetas. Or it can be an F term, meaning it can't be so written. For example, an F term in our case might be an integral over 4x's and 4 thetas of some operator O. But it can't be any old operator, because if you had any old operator and only integrated over 4 thetas, you wouldn't get a supersymmetric expression. It's only if O is independent of the theta bars that you get something supersymmetric by not integrating over them. Conversely, if O is independent of the theta bars, you'd get 0 if you tried to integrate over them, because of the basic rule of fermion integrals, that the integral of the theta bar of a function that doesn't depend on theta bar is 0. So chiral interactions like this one, or F terms like this one, correspond to chiral superfields, operators that don't depend on all of the thetas, on the theta bars, sorry. Now, as again Natty explained in the first lecture, it's usually only about the F terms that you can make non-perturbative statements, and my lecture today is concerned with F terms. In the case at hand, for every genus from 0 to infinity, there's a possible F term that I've written as follows. So I'm going to hide a few details to simplify things, but the basic idea is as follows. We have a bunch of spinless chiral superfields, so we can take any function at all of them. And then we've got some spin 1 chiral superfields, so we have to contract their indices to make a Lorentz singlet, but once we do that, we can raise it to the gth power. So basically, for every g, we can make a function like this. All I've really done is to write down the most general Lorentz invariant function of x and the w's. Since the w's aren't Lorentz invariant, we have to square them, and then we could raise them to the gth power for any non-negative g, and multiply by a function of the x's. So that's the most general F term we can make from the chiral superfields I've told you about. And these particular interactions have an amazing property. In type 2, remember, these are interactions that can arise in type 2a superstring theory. But in type 2a superstring theory, they have the incredible property that I sub g can only arise in genus G. The proof just follows from low energy supergravity. So I've written this formula in the Einstein frame. To compare to string perturbation theory, you make a Weyl transformation to the string frame, and then you find that this interaction is proportional to a certain power of G string, and therefore it can only arise in a certain order of perturbation theory. So I sub G is completely knowable for every G. All you have to do is integrate over the moduli space of genus G Riemann surfaces. Now, B, C, O, and V, Berchatsky, Ceccotti, Ugri, and Vafa, had an amazing insight about that integral. Because integrating over the moduli space of genus G Riemann surfaces is still a tough order, but their amazing insight was that the function fg that appears here is the same as the topological string free energy. Sorry, I keep writing partition function. As the topological string free energy, if you take the topological string couplings to be the ratios xi over x0. Remember, there was one special U1 gauge field that came from 10 dimensions. That's the one that appears in x0. There are all the other guys that arise in compactification. So there are ratios xi over x0 that are in one-to-one correspondence with the gauge fields that come from compactification, and those are also in one-to-one correspondence with the topological string couplings, And BCO and V says that if you set the topological string couplings to these ratios, then the topological string free energy in genus G, Fg, is the same as the function Fg that comes from type 2a superstring theory. So, okay, the statement in parentheses here is what I just told you. X0 is the multiplet that comes from 10 dimensions, and the other guys correspond to vector fields that arise from dimensional reduction. Now, this was actually already known for G equals 0, but the generalization to arbitrary G is quite remarkable. Unfortunately, at present, the only complete proof is rather technical. It's by Antoniadis et al. If you wanted to learn about the proof, you could look at this rather technical argument, but there's a not completely general but extremely simple argument you can find in a paper by Beasley and me. So if you wanted to understand why the statement is true, even though you won't learn everything, if you want to learn part of it quickly, you could look at a simple argument that Beasley and I gave. Technically, we gave that argument in the case where everything is completely non-degenerate. But I don't want to take the time here to explain what that means. Now, I will maybe stop, though, just for a second, if there's a quick question. Okay, what did Gopakumar and Vafa add to this story? Well, they said you should reinterpret this story in terms of M theory. So you should view type 2a on R4 times y in terms of M theory on R4 times a circle times y, where people sometimes call S1 the M theory circle. In this correspondence, the string coupling constant is determined by the radius of the M theory circle. Since I sub g for given g, so remember I sub g is this particular chiral coupling, since it has a known dependence on G string, its dependence on the radius of the circle is also known, and we can calculate in the region where the circle is large and the M theory description is useful. So that's what we get because there is a known dependence on G string. We can completely calculate in string perturbation theory, but we can also, it turns out, completely calculate in the strong coupling limit. Now, in string perturbation theory, F sub g comes from genus G string worldsheets, which get wrapped on a submanifold sigma and y, and the relation to topological string theory says that the important sigmas are holomorphic submanifolds. So, hopefully you know that a superstring worldsheet sigma corresponds in M theory to an M2 brane whose worldsheet is a circle times sigma, where S1 is the M theory circle. And in weakly coupled string theory, the circle is so little you don't notice it. And averaging over the circle, you interpret the M2 brane worldsheet as a string worldsheet. But now we go to strong coupling, using the fact that we're computing things whose dependence on the coupling is known, so we can go to strong coupling and compute them. If the circle is large, we take a completely different point of view and think of the circle as the time direction. We introduce a Hamiltonian that has states propagating around the circle. So an M2 brane wrapped on sigma times a circle can be studied in a Hamiltonian formalism in terms of states propagating around the circle. So it must be possible to compute the F terms I sub g by summing over contributions of wrapped M2 brane states. It may be intuitively obvious that if you're trying to generate an F term, you need to consider what are called BPS states, which means states, quantum states that are invariant under some supersymmetries. I'll give a technical explanation in a little while, but I don't want to leave you hanging, so for the moment I'll give a naive explanation. BPS states are quantum states that are invariant under some supersymmetries, and they can generate terms in the effective action that are integrals of operators that are invariant under some supersymmetries, in other words, F terms. A non-BPS state that isn't invariant under any symmetries, when it propagates around the circle, generates only an operator not invariant under any supersymmetries, in other words, a D term. So in other words, the state is going to generate an operator with the same properties. So it may or may not be that this is intuitively obvious now, but I'll try to make it intuitively more obvious. Well, I'll give a technical explanation later, and hopefully it'll come to seem intuitively obvious. But Gopakumar-Vafa made a further contribution. They had a remarkable idea on how to compute the FG. Their proposal was that instead of looking at the FG one at a time, you should study the whole sum. Well, what is the whole sum? All we know so far is that the whole sum is the integral over a part of superspace of an arbitrary holomorphic function of all the chiral superfields we've been talking about. All that this expression is a holomorphic function that's Lorentz invariant. So the indices here are contracted. And, well, we've made a power series expansion of it around W equals 0. But they suggested that this sum should be viewed as the superspace effective action evaluated in a background in which a constant anti-self-dual graviphoton field is turned on. So they said, turn on a constant gravitational field in space-time, calculate the effective action, and that's going to be this. And they also said that the superspace effective action should be computed by a one-loop calculation, summing over one-loop diagrams with BPS states running around the loop. And that calculation is supposed to be, okay, so they wanted to do a one-loop calculation where you sum over one-loop diagrams with a BPS state running around the loop in a constant graviphoton background. Whenever I say constant graviphoton background, since the graviphoton is a gauge field, what's constant is the field strength, not the gauge field. And the calculation is supposed to be a supersymmetric variant of a famous calculation by Schwinger. Schwinger computed the one-loop effective action due to a charged particle. He was interested in electrons in a constant magnetic or electric field. And one was supposed to imitate that for a BPS particle in a constant graviphoton background. And it's supposed to get a formula, which is the Gopakumar-Vafa formula. So the upshot would be to express the interaction curly I as a sum of contributions of BPS states. And Gopakumar-Vafa wrote down a formula, which I call the GV formula. And it's had all kinds of applications and enormous success. It's widely used, for example, by mathematicians who don't have the faintest idea where it came from. Now, there's a cousin of this formula due to Ugri and Vafa, which I wish I had time to explain in detail, but I don't. In this case, I'll just say what the context is, but I won't go farther. You still consider type 2a on R4 times y, where y is a Calabi-Yau threefold, but you add D4 branes on R2 times L, where R2 is an R4, and L is a Lagrangian submanifold. And again, you can now write some new chiral interactions, some new F terms that live on R2. But it would take too long to explain the details. But again, Ugri and Vafa said you could compute those F terms by lifting to M3. The M3 lift is now R4 times Y times the M3 circle. The D4 branes turn into M5 branes. And you calculate the F terms that live on R2 by looking at M2 branes that propagate around the circle. But now these are M2 branes that are bound to the M5 brane. So certain chiral interactions in type 2a can be computed in M theory by counting BPS states that live on the M5 branes. And what I'll tell you today has a complete analog for the Ugri-Vafa formula, but there just won't be time to go in that direction. Now, I will explain a computation that leads to the Gopakumar-Vafa formula, and I won't actually write down the formula in advance. We'll see what the formula has to be when we do the computation. But first, I want to address some general questions. Now, the very first question you should ask is whether there's any hope of doing this calculation at all. You have to ask whether the interactions Ig could come by classical dimensional reduction from 5 dimensions. A yes answer would mean what we're trying to do is hopeless, because you'd have to know the 5-dimensional effective action, which we don't know. And a Schwinger calculation in a magnetic field in 5 dimensions isn't going to tell us what was happening microscopically in 5 dimensions. The 5-dimensional effective action is input to the Schwinger calculation. So the Gopakumar-Vafa strategy will only tell us what happens in 4 dimensions that didn't happen in 5 dimensions. What happens as a result of compactifying on the circle and turning on the graviphoton background. So to the extent that the Ig can arise by classical dimensional reduction, we can only determine them by knowing what there was in 5 dimensions. But the IG do not arise from 5 dimensions by classical dimensional reduction. There are a couple of exceptional contributions to I0 and I1, which can arise that way, but actually those contributions are known. We know barely enough about M theory to know them. And otherwise, the IG cannot arise by dimensional reduction from 5 dimensions. I won't give a complete explanation of why the IG can't come from 5 dimensions, but a partial explanation that at least is short is this. The superfields X lambda contain axion-like modes that decouple at 0 momentum in any interaction that arises by dimensional reductions from 5 dimensions. But the interactions IG spoil this decoupling, so they can't arise by classical dimensional reduction. So I've cut some corners. Okay, I simplified slightly, but that'll at least give you a first orientation of why you can't get the IGs from 5 dimensions. And we need to know that before we get started. So in principle, we can do the calculation we want to do. That's good news. The next basic question is whether a supersymmetric background with a graviphoton field turned on does exist. A no answer would mean we could not get anywhere. In field theory, we could compute an effective action in an arbitrary background that's not necessarily supersymmetric or a solution of any classical equations of motion. Now, one problem is we don't really know how to do that in string/M theory, but that's actually not the worst problem. The worst problem is that even if we could do such a calculation, we couldn't learn anything from it. The reason is that in a non-supersymmetric background, in which, say, there's a superfield S whose integral over the theta bars is non-zero, it's hard to tell the difference between an F term like this with some chiral superfield phi. I have to tell my granddaughter's app to not turn on when I'm giving a lecture. It's hard to tell the difference between a chiral superfield, it's hard to tell the difference between an F term, where F is a chiral superfield, and a D term like this. Because given that the integral d4 theta bar of S is not zero, this would actually have a contribution that would look just like this. And you could try to distinguish them by going to higher orders, but if you think about it, you'll discover that that won't actually help, because you can also get confused in higher orders. So you can pursue my line of thought farther, but you'll see that you can't learn anything about F terms by expanding around a background that isn't supersymmetric. Plus, in string/M theory, we can't expand around a background that isn't a classical solution. So we can only learn about F terms by expanding around a supersymmetric background. In field theory, maybe we could use a background that's supersymmetric but not a classical solution, but probably we would not understand how to do that in string/M theory. I can't say for sure. Maybe it would involve something new. There aren't any results like that, but maybe it could happen. But at a minimum, we need a supersymmetric background. So, well, okay. So there's a naive reason you might think that it will be okay because, okay. First, okay. What you should worry about is that when you try to turn on the self-dual graviphoton, it might produce back reaction, meaning other fields will also be turned on. Well, in that case, you need to know what those other fields are, and they will affect the propagation of the M2 branes, or the BPS states. And if you can't make a background that way, that's supersymmetric, then you can't learn anything for the reason I explained here. But even if you can make a background that's supersymmetric, you need to know what it is. In other words, if turning on the graviphoton background results in back reaction on other fields, you need to know something about the other fields to understand your one-loop computation you eventually want to do. So we can't just say we'll calculate in a hypothetical background. We need to know that the background we're going to calculate in exists, and we need to know something about it. Now, if we turn on an arbitrary linear combination of anti-self-dual U1 gauge fields, we'll get no gravitational back reaction, since the energy momentum tensor of a self-dual or anti-self-dual Maxwell field vanishes. But generically, we'll get scalar back reaction, because there are a lot of scalar fields in type 2 Iona Calabi-Yau, and scalar fields couple to bilinears in F that are non-zero, even if F is self-dual or anti-self-dual. So generically, we'll produce scalar back reaction, and then we won't know what to do. But it turns out that scalar back reaction is avoided and moreover the background is supersymmetric, precisely if what one turns on is the graviphoton and not any of the gauge fields in vector multiplets. That's why we're going to get a useful answer that depends on only one background gauge field, the graviphoton. We can turn on the graviphoton, W, while preserving supersymmetry, but we can't turn on any of the other vector fields, gauge fields in vector multiplets. So a supersymmetric classical solution with the necessary properties actually exists. It's actually most easily described as a solution in a 5D spacetime with Lorentz signature. So we'll modify that a little bit, but I'll first write it down in its most physical form. It was discovered in 2003 by Gauntlet et al. They called it the supersymmetric Gödel solution. It's given by this very simple formula. There's flat R4, and then there's a time direction, and then T minus is a constant anti-self-dual 2 form that in our interpretation is the graviphoton. And then V mu is the gauge field of the self-dual graviphoton, except, well, it would be conventional to have a factor of 2, so V mu is a quarter of the gauge field. And this simple thing is the metric. And they called it a Gödel solution because it actually has closed time-like curves, because of the minus sign multiplying V squared x squared. Now, it's weird because it has closed time-like curves, but it's a completely real solution. To use it in M-theory compactification to type 2a, we need to compactify the t direction, but also we want the metric on the circle to be Euclidean, because the M-theory circle is supposed to be Euclidean. So we rotate t to iy, where y is a periodic variable. But then you see that that'll cure the minus sign in front of dt squared. But if we keep v as it is, this part of the metric will become imaginary. The metric will stop being real. So in Euclidean signature, the metric, and it's impossible to make both the graviphoton and the metric real, the lesser evil is to make the graviphoton imaginary so that the metric is real. The reason that's the lesser evil is that we'd be uncomfortable, possibly, with trying to do a calculation on a space-time with a complex metric. But there actually isn't a serious problem in doing a calculation where a background gauge field is not real. One thing that might make it obvious is that the interaction we're computing, we actually expanded it in a power series in powers of W. And order by order in perturbation theory, if an external photon has an imaginary wave function, it doesn't keep us from doing perturbation theory. Another explanation is that Schwinger's original calculation worked fine in either an electric or magnetic field. An imaginary magnetic field in Euclidean space is rather like the real electric field in Lorentz signature that Schwinger actually studied. So anyway, the background that we need for the Gopakumar-Vafa calculation exists. It's not real. And it turns out later on that the fact that the background isn't real avoids some puzzlements one might have had about their formula. The background has a remarkable property that was discovered by Gauntlet et al. And from a different perspective by Berkovits and Seiberg. Berkovits and Seiberg were not working in 5-dimensional supergravity. Their point of view was completely different. Naively, if you turn on an anti-self-dual gauge field, you preserve at most 1/2 of the supersymmetry, which in our problem would mean preserving 4 of the 8 supercharges. But it turns out that the supersymmetric Gödel solution preserves all 8 supercharges that you would have before turning on the graviphoton field. That's really quite remarkable, and one ought to ask, well, what is such a striking fact good for? Which we'll discuss later, or maybe I'll show you in a moment. So you preserve all 8 supercharges, but the supersymmetry algebra is deformed from what it is before turning on the graviphoton. So you find out, for example, that the momentum operators no longer commute with the supercharges, and so on. The algebra is modified, but the number of supersymmetry generators is not changed. So from my point of view, the reason that the extra supersymmetry is important is the following. It turns out that to compute the GV formula, you need to know the magnetic moments of the BPS states. And the unexpected extra force supersymmetries and the deformed supersymmetry algebra turn out to uniquely determine the magnetic moments. And they enable you to get the universal Gopakumar-Vafa formula. If you didn't have the extra force supersymmetries in the graviphoton background, you wouldn't be able to justify the universal magnetic moments that you need. Now, there are a few more questions we should ask, and I won't have time for all of them, but here's another one. Quantum mechanics has wave-particle duality, but the range of validity of a calculation based on waves can be quite different from that of a calculation based on particles. So, is the Schwinger calculation that leads to the GV formula supposed to be a calculation based on particles or on fields? Well, to answer this question, we have to think about what we actually know about M theory and where our approximations are valid and what calculations we can do properly. So to the extent we understand M theory, we understand that when the length scales involved are much greater than the Planck length. By the way, there's something I regard as rather pretty here, which we only learn if we make sure that our approximations are valid. We actually can do all the calculations we need to do, just barely, and different ones for slightly different reasons. So you see, we only understand M theory when the length scales involved are much greater than the Planck length. So we should think of the Calabi-Yau manifold Y as much bigger than the Planck length, and a massive BPS state coming from a wrapped M2 brane has a mass much bigger than M Planck. Now that's a hint we shouldn't try to use field theory to describe it, because we would be wary of using field theory to describe a particle that's much heavier than the Planck mass. But even if you want to do field theory, you're going to have trouble, because wrapped M2 branes can have arbitrarily large spin in space-time, and for particles of spin 2, greater than 2 rather, coupled to the background supergravity multiplet, it's not clear we have a sensible field theory to use. So you've been hearing lectures on higher spin by Jambi, and you can try to apply what you've learned and find a sensible wave equation for a particle much bigger than the Planck mass with a spin of 92, coupled to the graviphoton background. But you should be suspicious of whether that's the right thing to do for this problem. Instead, we're going to do a particle calculation for BPS states that are massive in 5 dimensions, and you'll see the particle calculation will be completely painless. It won't raise any of the worries that I think you ought to have if you try to do the calculation for a particle with spin 92 and mass much bigger than the Planck mass by representing it in terms of fields. We only will use field theory for the very few BPS states that are massless in 5 dimensions. I'm actually only going to do the calculation in front of you for the massive case, which means all but finite many of the infinitely many BPS states. There are these massless stragglers. You see, if a guy is massless, that means its Compton wavelength is big, and field theory is good. After all, why do we know about field theory? We know about field theory because it's good at long distances, and we make our observations at long distances. And for the massless particle, it propagates long distances. So we can treat the massless particle by field theory, and we actually would have trouble treating it by particle theory because we probably don't know a superparticle action that would be convenient for this calculation. Though I'm actually in part tossing that remark out in the hope that somebody will prove me wrong. I'd like to see how the superparticle calculation would go for the massless modes. But anyway, it can't be done by the simple argument I will give you for the massive ones. So to recapitulate, what we know is just enough. For the massive guys, there will be a simple particle calculation. The massless guys have spin no bigger than 2. They're massless, and they have sensible field theories, and the field theory calculation is good. So what we'll actually do is the particle calculation. So we start by thinking of the M2 brane wrapped on what? Well, it's wrapped on a Riemann surface sigma and y, and then there's a circle in the S1 and a point in R4. But here I'm not trying to draw y or sigma. So I'm just drawing p times S1 in R4 times S1. And R4 I'm just drawing schematically, horizontally. S1 goes this way. And that's a point in R4. And this red dotted line is a point times a circle. So we're going to think of the particle propagating around the red circle as a kind of instanton. That's an event that happens in space-time. It's localized in space and time at a point P in R4. So a Yang-Mills instanton happens at a little localized region in Euclidean space-time, and this event happens near this point in Euclidean space-time. The classical picture makes it look like it happened at a point, but of course this is a quantum particle, so it's always fluctuating a little bit around the classical orbit. But still, it's localized in space-time, and so we should think of it as an instanton, somewhat analogous to a Yang-Mills instanton. Now, in drawing the picture, I actually ignored sigma and just depicted the M2 brane world volume as a particle world line in P times a circle. And that's actually the right thing to do in the following sense. If the circle is big enough, then, which is the limit where our approximations are going to be good, we can ignore the internal structure of the BPS state and the existence of the compact manifold Y, and just think of the BPS state as a point particle propagating in R4 times a circle. We're measuring the effective action in R4 at low energies. We don't have the capabilities of resolving the details of Y or the internal structure of the BPS state. So it will be sufficient to just say that there's a BPS particle that propagated around a circle and that we'll interpret as determining an instanton in R4. So we view the particle winding on P times a circle as a sort of instanton in 5-dimensional supergravity on R4 times a circle. I should say there are a lot of calculations like this where wrapped branes are interpreted as instantons. Of course, it's older in the context of world sheet instantons in string theory, but for branes such as wrapped M2 branes, an important early paper was by Strominger and the Beckers in 1995, or perhaps 96. Now, to get the effective action, we have to integrate over the moduli of the instanton, and of course, over any other degrees of freedom as well. The simplest case is that the only moduli of the instanton are the ones that have to exist because of translation invariance and supersymmetry. There might be more moduli, and then in our paper we'll discuss the implications, but for today's lecture, we only will consider the simplest case with only the moduli that exist because of symmetries. The instanton inevitably has at least 4 bosonic moduli associated to translation symmetry. They are the coordinates x mu of the point P in R4 at which the instanton lives. If the particle is not BPS, if it is not invariant under any supersymmetry, then its world line is not invariant under any linear combinations of the 8 supersymmetries, and the 8 supersymmetries will generate 8 fermionic moduli of the particle world line. I'll call these 8 fermionic moduli theta AI and theta A dot J, where I use the fact that they have the same quantum numbers as the supersymmetries. So there are 2 sets of negative chirality moduli and 2 sets of positive chirality moduli. Thus, for a non-BPS particle, the effective action will be integral d4x d4 theta bar times O, where O is the instanton amplitude without integrating over the moduli generated by the space-time supersymmetries, but after integrating over anything else, including any other moduli there may be. So you see that a non-BPS particle will generate a D term. What about a half BPS particle that's invariant under the 4 supersymmetries of positive chirality? That's what you get from a BPS particle wrapped on it, comes from an M2 brane wrapped on a Riemann surface. For such a particle, we only have 4 fermionic moduli, so the effective action is going to be d4x d4 theta times O, where again, O is whatever we get by integrating over everything else. In other words, a half BPS particle can generate an F term. I should have written can rather than will, because something that can be written this way maybe can also be written as integral d8 theta of something. So we're not guaranteed to get an F term, but we might get an F term from a half BPS particle. In fact, most of the stuff we get will not be F terms. It's only special contributions, even from the BPS particles, that will be F terms. But this shows that only BPS particles can contribute to the GV formula. The BPS particles that have no moduli except the ones forced by the symmetries are massive hypermultiplets that come from an M2 brane wrapped on an isolated genus 0 curve in Y. And since I don't want to talk about any additional moduli except the basic ones, we actually will only discuss the calculation for this special case. However, I will say that once you understand this case, it's a little bit longer, but you don't need to know very much more to do the general case. Let's analyze the contribution of such a particle. First, we need to understand its mass. The Kähler form of Y, which I call omega, can be expanded as a sum of harmonic forms omega I. We used them before in the Kaluza-Klein expansion for the M3 form, where the coefficients are Kähler moduli. I'm going to take some very slight liberties to avoid some details. The charges of the BPS states are its winding numbers, Qi, which are the integral over the world sheet of the M2 brane of omega I. We abbreviate the whole set of charges as Q vector, which I called D vector at the beginning of the lecture in the topological field theory language, but now we want to think of them as charges by which the particle couples to gauge fields, so I prefer to call them Q. The area of sigma is the central charge, which is the sum of the moduli H times the charges Qi. This formula just comes from the fact that zeta is the integral of omega over the world sheet. And if you use this expansion for omega and this definition of the charges, you get a formula for the central charge of the BPS state. So in units in which the M2 brane tension is 1, the mass of the BPS state, well, the mass of the BPS state is the same thing. We should take the absolute value, but we don't have to, because zeta is positive. It's real in any way in 5 dimensions, and it's positive for a holomorphically wrapped M2 brane. So the mass is just zeta, and zeta is this. Now, we also need to know, as well as the mass, how the BPS state couples to gauge fields. The 5-dimensional theory has gauge fields AI that I introduced at the beginning, and it has corresponding magnetic fields Fi. In the graviphoton background, the magnetic fields are the moduli, the Kähler moduli, times the graviphoton. Now, I've written in red an explanation of this. So I didn't want to make the lecture clumsy at the beginning, so I only wrote down the supersymmetric Gödel solution the way that actually Gauntlet wrote it down, for pure supergravity without vector multiplets. You have to embed that solution in a model that also has vector multiplets, and to make that embedding, you need this formula. Okay, let's go back to black. The effective magnetic field seen by a particle of charge Q is F of Q, which is the sum of the charges times the magnetic fields. But since the magnetic fields are this, the effective magnetic field seen by a guy of charge Q is QiHi times the graviphoton, but QiHi was the central charge, and the central charge is the mass. So the magnetic field seen by any particle that's BPS is the mass times the graviphoton. So why is the magnetic coupling proportional to the mass? Well, intuitively it happens because the graviphoton is in the supergravity multiplet, and gravity couples to mass, and for BPS states, the graviphoton couples to mass also. That's what this formula says. So the fact that the effective magnetic field depends only on its mass is very important in getting the GV formula. Now let's discuss the action for the BPS particle. Well, what are the terms we know about? So first of all, when the circle is very big, we only will have to treat the BPS particle non-relativistically. That's because if the circle is very big, you can make an expansion in 1 over the radius of the circle, and you can show that only the leading term contributes to the chiral interaction we're looking for. The instanton will contribute additional amplitudes that are suppressed by powers of 1 over the radius, but they are not F terms. The F term comes from only the leading contribution for large radius. And to get the leading contribution for large radius, that means the BPS particle is propagating for a very long time. A massive particle at rest for a very long time can be treated non-relativistically. It'll just fluctuate a little bit around the static orbit, the classical orbit. So what is there in the action? Well, there's a very large constant non-relativistically, minus mc squared, although we're going to set c to 1 henceforth. And we shouldn't forget the usual non-relativistic kinetic energy, which is half mx dot squared for bosons. And so there are bosonic collective coordinates that are generated by the broken translation symmetry of the particle, but there also are what you could call Goldstone fermions on the particle world line. The particle is not invariant under all the supersymmetries, only under half of them, and the supersymmetries under which it's not invariant generate Goldstone fermions that live on the particle world line, and I've written down the minimal kinetic energy for Goldstone fermions. So the minimal action we could write is minus the mass plus the non-relativistic kinetic energy plus the free kinetic energy for Goldstone fermions. And you could add all kinds of corrections, and in fact, physically there are higher corrections, but they're irrelevant when the radius of the M-theory circle is large. They're irrelevant in their normalization group because they have higher because they have higher dimension, and you can show that they don't contribute to the F terms because their contributions have extra powers of 1 over r that an F term wouldn't have. So until we turn on the graviphoton, this is a good enough action. And we can verify its supersymmetry. So what is the supersymmetry algebra? Well, there's translation symmetry and there are supersymmetries. So the translation generators are just the conserved momenta, mx dot, and of course they commute. Well, here are the supercharges. Since the psi's are Goldstone fermions for the supersymmetries under which the particle is not invariant, that means that half the supersymmetries have to be able to create psi from the vacuum. They're linear in psi. And again, we don't care about the higher order terms, which are irrelevant in the normalization group sense. And by hand, you can, since P is conserved and Q is conserved, P times Q is conserved. So by hand, we can make 4 more conserved supersymmetries. And with a very short calculation, you can show that P, Q, and this kind of Q generate the supersymmetry algebra that you know from textbooks with this Hamiltonian, mc squared plus p squared over 2m. So it's straightforward to verify the appropriate supersymmetry algebra, except that you get the non-relativistic limit of the supersymmetry algebra because we took, well, for example, this is the non-relativistic approximation to the Hamiltonian. Now let's turn on the graviphoton field. There's one obvious term we need in the action. The BPS particle is charged, so, well, the action for a charged particle coupled electromagnetically is the integral dt of the vector potential times x mu dot. But in this case, the gauge field is the sum of q times these gauge fields, and moreover, A is the gauge field of a constant graviphoton. So the term we actually have to add can be written just in terms of the graviphoton. See, I hope you recognize that for a particle in a constant magnetic field, the action is the field times x dot. So I've just written x dot times the field, where I explained before that the field is m times the graviphoton. So hopefully you recognize that as the action for a charged particle in a magnetic field, a constant magnetic field, T minus, with the slightly unusual property that the mass plays the role of the charge because a BPS particle couples to the graviphoton through its mass. So the most minimal action we can think of is, well, you have to remember the rest mass appears with a minus sign in the action. It's part of the potential. Then there's kinetic energy and kinetic energy of fermions. And then there's the coupling to the graviphoton. So the action has to at least contain that much. And it turns out that's all there is, modulo irrelevant terms of higher dimension. We should spend a couple minutes discussing what is the appropriate scaling symmetry, but after a little while, we'd see that anything we could add here would be irrelevant in the renormalization group sense and will contribute in the wrong way to give F terms. Now, if this is the only possible action, it had better have the right supersymmetry algebra. What supersymmetry algebra does it have? So probably you know from your studies that in the presence of a constant magnetic field, for a charged particle, quantum charged particle, there's still translation symmetry, but the translations don't commute. So in fact, in the presence of a constant magnetic field, the conserved memento p mu are no longer the canonical momentum little p mu. There's a correction term, and hence the conserved memento no longer commute. That's the standard formula for a particle in a charged particle in a magnetic field. The only difference being that, again, what plays the role of the charge is the mass, because we're discussing a BPS particle coupled to the graviphoton. It turns out, oddly enough, that the old formulas for the superchargers are still correct. They're obviously still conserved. Psi is still free. Since psi is free, the equation of motion for psi is psi dot equals 0. In other words, psi commutes with the Hamiltonian. So if q is m psi, then q still commutes with the Hamiltonian. And if p and q are conserved, then p times q is still conserved. So I've exhibited 8 conserved supercharges for this action. But since the definition of p mu has changed, the algebra they generate is deformed in precisely the way seen in supergravity. So you see, you're accustomed to p commuting with the supercharges. But since p doesn't commute with itself, p doesn't commute with this one of the q's. P with p is a C number, so p with this q is going to be psi, in other words, this q. So p with supersymmetry of positive chirality is a supersymmetry of negative chirality, as was actually first found by Gonzlet et al. In the supergravity solution. So now let's evaluate the path integral for fluctuations around the particle trajectory p times a circle. Well, what's the path integral going to be? One factor is certainly the exponential of minus the classical action. Then we have to do a path integral over fluctuations. But since our action is quadratic, the path integral is just a ratio of determinants. So I wrote the square root of the fermion determinant divided by the square root of the boson determinant. But actually, there are zero modes in both determinants, which is conventional in instanton physics. Unfortunately, I forgot the primes here, which I explained over here. Except I put the prime. It's supposed to be determinant prime of d sub f and determinant prime of d sub b. Okay. There are a few misprints, sorry. I should better just explain it in words instead of trying to fix all the misprints in that slide. In instanton physics, you can't literally take the determinants for the one-loop fluctuations because there always are zero modes. You want to use the determinant prime, which is defined as the product of all the non-zero eigenvalues. And then the zero eigenvalues are treated by integrating over the moduli. So what we're going to get is an integral over the moduli that means an integral d4x d4 theta, an exponential of minus the classical action, and then a product of determinant primes, meaning determinants with zero modes removed. The only zero modes are the ones associated to these space-time symmetries because we decided to discuss the case in which those are the only moduli. Otherwise, in general, we'd have more moduli and a slightly longer discussion. So I've already said this, but as usual in instanton physics, we remove the zero modes from the determinants and replace them with an integral over the moduli or collective coordinates, which here are x and theta. So the integral over collective coordinates might give an f term. The only reason I say might is that on a bad day, this expression would be d4 theta bar of something else. But on a good day, this would be an f term. And the leading term, the term which dominates for large R, where the circle is very big, that happens to be a good day. So we get an f term. So I'll very quickly explain how to evaluate these terms. So first we'll discuss the classical action. One obvious term in the classical action is the mass times 2 pi times the radius. In other words, times the circumference of the M3 circle. But there's one more term in the classical action that arises once we compactify on a circle. We should allow for the possibility that the gauge fields can have monodromies around the circle. So these parameters are important in the type 2a description. They're the real parts of the chiral superfields that we discussed before. So at the beginning of the talk, when we were doing 4D supergravity, the chiral superfields we discussed included these monodromies. So if we want to make contact with them, with that part of the discussion, we should include them now. In the presence of these monodromies, a particle of charge qi going around the circle picks up a phase. And we should think of that we should take that along with the exponential of minus what we got from the mass. And something happens, which is a part of the Gopakumar-Vafa story, which is that this product is just the exponential of minus 2 pi I times the charge times z, where z is the ratio of two of those chiral superfields. Z is basically one of the chiral superfields in 4 dimensions, or more exactly, it's a ratio of the chiral superfields that I had used earlier in the lecture. Gosh. So our answer is going to be, another misprint, unfortunately. This alpha should be z. Our answer is going to be d4x d4 theta times this factor times what we will get from the one-loop determinants. We still have to evaluate the determinants, but I decided I wasn't quite going to do it in front of you. I'll just talk about it a little bit. They are the simplest functional determinants you're ever going to see, so if you've ever evaluated any kind of determinant, you may have evaluated these. The fermionic determinant is completely trivial, since the fermions are free. The fermion operator is ID by dt. And the boson determinant is also a classical example, since the boson kinetic energy can be factorized in terms of minus d by dt and d by dt plus the graviphoton, which is a constant matrix. So the determinants we have to compute are either the determinant of d by dt or the determinant of d by dt plus a constant. You can literally just diagonalize this matrix and just replace it by a constant number. So the operator whose determinant you have to compute is d by dt plus a constant number. So if you ever calculate any functional determinant, even if you can't remember doing it, if you ever calculated a functional determinant as a student, you probably computed that example because nobody could have given you a simpler example. So after a little work, you get a result that's part of the Gopakumar-Vafa formula. I keep miswriting it. I wish I would later write it correctly, but maybe I kept copying this. Alpha should be zi, the chiral superfield. And then it multiplies t squared over sinh squared of pi r times t, where t is this. Now, this probably doesn't quite look holomorphic. You could ask me what R is doing there. If you reduce to 4-dimensional language, you find out that this magically turns into the thing we had before with the superfield W, curly W. One has to add further contributions from the case that the BPS particle wraps k times around the circle for k bigger than 1. Well, what does that do? Well, the particle is propagating k times as far, so the classical action is multiplied by k. The effective radius is also multiplied by k because the particle is going k times as far, but you have to divide by k because of the k-fold cyclic symmetry among the different sheets of the particle orbit. So you get this formula. Unfortunately, alpha should still be curly z, as the contribution to the GV formula of a massive BPS hypermultiplet of charge q. So if figured I'd be running out of time, but you see, it would be a good exercise. Okay. Well, I've gone through this too fast to give you the time to worry about something you should have worried about if you had more time. M2 branes are strongly coupled. You should ask why, when the M2 brane wraps multiple times around the circle, we can ignore the interactions among the different branches. It's a non-trivial point. You have to show that the M2 brane interactions are irrelevant in the renormalization group sense, even though they're strong at short distances. And all they can do that might be important is to produce a bound state that then itself would contribute to the GV formula. So we still have to go on and analyze the contribution from other BPS states, but we don't really have time. For massive BPS states that aren't in hypermultiplets, the idea is the same, although there are a few extra details. You use supersymmetry. It's very important that the graviphoton preserves 8 supersymmetries to determine the appropriate Hamiltonian, and then you compute much the way I described. For those few BPS states that are massless in 5 dimensions, the instanton point of view doesn't work, but as I mentioned before, there's a different simplification. Those modes just come from 11-dimensional supergravity, and so therefore they have spin at most 2. And we do have a good field theory for them, namely 11-dimensional supergravity. And actually, since they arise as zero modes along y, which is why they're massless, you can do the calculation in 5-dimensional supergravity. So to study the massless modes, you compute one-loop determinants in the 5-dimensional graviphoton backgrounds. You can conveniently do this computation by reducing to 4 dimensions on the M-theory circle. So then you have to calculate 4-dimensional one-loop determinants of massive BPS states with different values of their mass. And here the calculation really is a sum over spins and masses of Schwinger's classic calculation for a 4D charged particle of mass m in a constant magnetic field. So that's what I have to tell you. Thank you.